So, you've built your app, you've containerized it, but have you ever stopped to wonder how Kubernetes decides which of its many servers is the perfect home for it? Well, today, we're going to dive deep into the brain of the operation, the Kubernetes Scheduler. It's the component that makes that critical decision every single time.
So, here's the big question, right? You've just created a new application container, what Kubernetes calls a pod. You know, the smallest thing you can deploy. It exists in your configuration files, but it's not actually running anywhere yet. So how does it get from just sitting there in a pending state to actually doing work on a specific server?
And that's the journey we're going to follow. On the left, you've got our pending pod. It's basically homeless, can't do any work. Our goal is to really understand the magic that gets it over to the state on the right, a running pod, assigned to a server or a node in Kubernetes speak and happily doing its job.
The hero of this whole story, the thing responsible for this entire transformation, is a process called the Kube Scheduler. You really should think of it as the brain, making all the crucial placement decisions for every single application you run.
You know, probably the easiest way to get your head around the scheduler is with an analogy. Just picture it as a super smart seating planner at a really busy restaurant. Your pods, your apps, are the customers who need a seat. And the nodes, your servers, are all the tables. The scheduler's entire job is to find the absolute perfect cable for every customer, making sure nobody gets overloaded and that everyone's needs are met.
Now, the scheduler doesn't just guess. It's got this super logical two-step process. First, it does something called filtering. It narrows down the list of all possible servers to only those that can run the pod. Then, once it has that shorter list, it does scoring to find the single best fit out of the candidates. All right, let's break down exactly how each of these phases works, starting with filtering.
Welcome to the elimination round. So in this filtering phase, what happens is the scheduler basically grabs a list of every single node in the cluster. Then it starts asking a series of simple yes or no questions to disqualify any that just aren't a good fit.
The most basic and most important check is for resources. When you define your pod, you tell it, I need this much CPU and this much memory. And that's a hard rule. It's non-negotiable. So the scheduler's first filter is dead simple. If a node doesn't have enough available CPU or memory to meet the pod's request, it's immediately out of the running. This is what stops one app from hogging all the resources and crashing the server.
Okay, next up, it checks for labels. You can actually tell your pod, hey, I only want to run on a machine that has a super fast SSD disk. And you do this with something called a node selector. The scheduler sees that and will immediately filter out any node that doesn't have that specific disk type SSD label you asked for.
And a final, really powerful check involves something called taints and tolerations. Now, you can taint a node to basically repel most pods. This is incredibly useful for dedicating specific hardware, like say a node with a powerful GPU, to only the workloads that actually need it. So you'd apply a taint like GPU equals true. And unless your pod has a matching toleration that says, hey, I'm cool with that, I'm designed for this, the scheduler will filter that node out. It's kind of like a VIP section at a club. You need the right pass to get in.
So after all these checks are done, we're left with a short list of what are called feasible nodes. Every single node on this list has passed all the basic requirements. And here's the key thing. If that list ends up empty, well, the pod can't be scheduled. It just sits there stuck in that pending state, waiting for a suitable node to maybe become available later.
All right, so we've got our list of contenders. Now we move on to the scoring phase. See, it's not enough for a node to just be able to run the pod. The scheduler wants to find the absolute best place for it. This is all about keeping the whole cluster healthy and running efficiently.
So, how does it decide? Well, it uses a bunch of scoring rules. For instance, it'll give a higher score to a node that already has the app's container image downloaded, because that means a faster startup time. It also tries to spread pods from the same application across different machines. That's great for high availability. And it loves nodes where the CPU and memory usage are nice and balanced, which helps prevent creating hotspots where one server is totally overworked while another one is just sitting there bored. And here's what that looks like in the end. After the scheduler applies all its scoring rules, each of those feasible nodes gets a final score. In our little example here, node C comes out on top with a score of 9. It's our clear winner. The decision is made. So the very last thing the scheduler does is what's called a binding. This is the official moment where it updates the cluster's state and basically declares, okay, this pod now officially belongs to node C. That decision gets recorded, the pod status gets updated, and just like that, the scheduler's direct involvement in this pod's journey is done.
But hey,
This whole thing isn't some magic black box you can't control. Nope. As a developer, you actually have a really powerful set of tools to influence these decisions. Think of this next part as your personal rulebook for guiding the scheduler.
This here summarizes the main tools you've got. Let's just quickly run through them. We've already talked about node selector for those hard requirements on labels. We also just covered taints and tolerations for that VIP access model. Now, node affinity takes it a step further. It lets you express preferences, like, hey, I'd prefer to run in this availability zone for lower latency, but it's not a deal breaker. Then you've got pod affinity, which is all about how pods relate to each other. You could use it to make sure your web front end and its cache run on the same server to cut down on network delay, or do the exact opposite and keep them separate for resilience. And of course, resource requests, the most fundamental rule of them all, telling the scheduler exactly what your app needs to run.
All right, that's a lot of theory. Let's make this super real. We're going to walk through the whole process from start to finish with a real-world example, scheduling a standard Nginx web server pod. All right, here's the YAML for our pod. Take a look right here, under the spec section. We're telling Kubernetes two really important things. First, under resources, we're requesting a quarter of a CPU core, or 250M. And second, under node selector, we are demanding a node that has the label disk type SSD. These are our direct instructions to the scheduler.
The second we apply this file, that pod goes into the pending state, and the scheduler immediately wakes up and sees these two key requirements, the resource request and that node selector. Its decision-making process kicks off right away.
Phase 1. Filtering. The scheduler zips through all the nodes in the cluster. Any node that doesn't have that disk type SSD label, gone. Instantly eliminated. Any node that does have the label but doesn't have at least a quarter of a CPU core free, also eliminated. Our list of potential candidates gets a whole lot smaller really fast.
And then, phase 2, scoring and binding. The scheduler crunches the numbers on the remaining nodes, picks the top one, and boom, it performs the binding. At that exact moment, the scheduler's job is done. The kubelet, that's an agent on the winning node, takes over, pulls the Nginx image, and starts the container. Our pod's journey is complete. It is now officially running.
And there you have it. That's the detailed breakdown of how the Kubernetes scheduler really works. It's this powerful combination of strict hard rules and intelligent preferences. So the next time you sit down to write a configuration file for a pod, think about these rules. How can you give clearer, more precise instructions to the scheduler to make absolutely sure your application lands in the perfect home?